Hi everybody! So today I want to talk more about Turing machines and what they entail. There's a couple of things that we're going to talk about, but let's start by talking about what it means to be a Turing machine. And the thing that I want you to remember is that a Turing machine has three possible outcomes. It could accept a string, it could reject the string, but it could also loop forever. And so we say that a language is Turing recognizable, or you can just write recognizable, if there is a Turing machine that can recognize it. So literally, can you make this Turing machine? It could loop forever, but at least it would accept the strings that are in that language. A language is decidable if that Turing machine is a decider, meaning that it halts on all inputs. And then the other thing I wanted to remind you is this use of the Langle and wrangle brackets, like the left angle bracket and right angle bracket, which is going to talk about how we encode objects into strings. So there is a way to write a Turing machine so that you can write it as a string, which means Turing machines can accept themselves. You can actually have a Turing machine as input to a Turing machine, because everything is just strings. And then kind of moving forward, we're going to talk about the way that we write Turing machines, which is going to be very much like code, only we need to think about the parts of a Turing machine, like the fact that it has a tape, to be able to write those algorithms. Okay, so with all that said, let's go ahead and talk about a particular problem that I might be interested in with Turing machines. This is a language. The language is the acceptance problem for DFAs. So inside the left angle and right angle bracket, I've written B, comma, W, where B is a DFA and B accepts W. So in some way, we have a encoding of B so that it's a string, and then we also have W. And that's what's going to go on the tape of that Turing machine. And so when I want to write this Turing machine and explain that this language is going to be recognizable or decidable, I'm actually going to write an algorithm. So the theorem that I'm going to have is a DFA, the language, is decidable. It's decidable because I can make a decidable Turing machine for it. So here's my proof. My proof is an algorithm. Let's construct the Turing machine that decides a DFA. So you're going to say it's an algorithm. On input S, I have my input, and then I'm going to have an output, which is going to be accept or reject. Okay, so on input S, first of all, I'm going to parse for correctness, making sure that the string that I have on my tape for my Turing machine actually has that form BW, where B is a DFA and W is a string. I can reject if it is not. And then I can simulate the computation of B on W. So we've done this before with DFAs, where we actually took a string and we ran it through that DFA. If B ends in an accept state, then we accept. If not, then reject. So the accept states for DFAs are encoded onto the tape of that Turing machine. So looking at that, we have this machine, the A DFA, and it's looking at this tape. The input tape somehow contains B and W, and so that's why it's important to remember what the definitions are. So remember, with the definition of a DFA, I want that tuple of the states and the alphabet and the transition function and the final states. I'm not really telling you yet what does it look like to put this on a tape, but there is a way to do it. Everything is strings. Now, we can additionally think about a work tape, which is what the current state is in the input head location. And normally the way that I might write that would be like with the little arrow pointing to the tape itself, and then I say what state we're in. So we're writing what our input is, and then we're simulating that computation. And that's it. This is a deciding Turing machine. Moving forward, it also turns out that if B is an NFA, and B accepts W, that is also another decidable language. And now we're going to think about a new technique for doing this, which is going to be the fact that we already know that A DFA is decidable. Okay, so my theorem is A NFA is decidable, and here's my proof. I'm going to write a Turing machine that decides A NFA. On input BW, so here, I'm not even going to bother with that parsing because I'm saying that my input is already good ahead of time. I'm going to convert the NFA B to an equivalent DFA B prime. We know that we can do this. We've seen this before with subset construction. Subset construction is an algorithm, which means we can run it on a Turing machine with a tape. And now, I already had the answer for the Turing machine ADFA, so I'm going to run ADFA as Turing machine on B prime W. And I know that DADFA decides ADFA. And I'll just accept if DADFA accepts and reject otherwise. And notice here that it's always going to accept or reject. That's how I know it's a deciding Turing machine. So the new kind of idea that we have here is that we're going to use conversion construction, which we have talked about before with subset construction, and the fact that we already had an answer for the Turing machine for the ADFA. You can use old DFAs as new DFAs in your as subroutines in your construction. And one of the key ideas that I really want you to get out of here is this concept of running subroutines. You may have written code where you need to write a method or a function that calls another method or a function, or you've done recursive algorithms before where they call themselves. These are all things that are also possible in Turing machines, right? Turing machines are just a way of writing code. You can even think of it as a kind of programming language. Let's look at another example, the emptiness problem for DFAs. And so what we notice here is that now my input is just the DFA. I don't have a string with it. And I'm going to say B is a DFA, and I want that language to be empty. Now, we could concoct the DFA for this, right? We've seen that before where we said maybe like we just have the state, and then in all the letters, it's just going to loop back in on itself, and it's a reject state. It's not an accept state, so it's going to be empty. That's great. It's the smallest DFA that you can have for that language, but I could actually create infinitely many DFAs that also recognize, that accept the empty language only. Even so, I can still say that the set of all of those DFAs, even though there's infinitely many of them, is decidable. So the way that we say like a language is decidable is by giving a Turing machine that decides it. And now we need to think about the idea. So thinking about some things that we might try here, we definitely want that input to be the DFA. And then the idea written here is check for a path from start to accept. When we're starting to think about the DFA being empty, or recognizing the empty language only, you know that it shouldn't have any accept states. And so that kind of gives you an idea of how to run this DFA to check it. How do you test it? Okay, well, maybe it has some accept states. Can you hit them, though? Are there strings that let you hit them? So kind of like going through and highlighting the states as we're reaching them, just because if there's an arrow, you can see what all states are reachable. The word is reachable. So the idea is we mark that start state, and then we keep repeating until we don't see any more new states. Mark every state that has an incoming arrow from a previously marked state. At the end, if the states that are marked are all reject states, in other words, they're not accept states, then you know that the language of this DFA must be empty. Let's look at another example. EQ DFA, so EQ for equivalence or equality, And here notice that my input is two DFAs, A comma B. So as long as I put these little angle brackets on the outside, that's indicating to me that I have some sort of string that I'm representing the DFAs with so that I can put it on the tape. So in this case, I want to have the DFAs and I want to ask if the language of those DFAs are the same. And this is also decidable. We are going to give that Turing machine that decides it. So the idea is we're going to construct a new DFA that accepts the strings where A and B disagree. Since I'm asking is L of A equal to L of B, I really just care about that intersection or symmetric difference. So I'm going to construct a DFA who accepts the symmetric difference of A and B. I'll run the empty DFA on C, and if it accepts, then I'm going to accept. Otherwise, no. Right? So noticing here that if I have an intersection that is empty, then they would have nothing in common, right, if the intersection is empty. So what I really need to say is that the intersection is equal to both of those languages. And one way to do that is by doing symmetric difference, which is it's in A but not in B, or it's in B but not in A, and then checking to see if it's empty. Okay. You could probably come up with another way to do this that would maybe take a little bit longer, using ideas with intersection and union that you know about DFAs. So because we previously proved those properties about DFAs, we can use them. All right, so here's like a little question for everybody. Let's say EQ Rex, R1 and R2 are regular expressions. Is it true that the language of R1 is equal to the language of R2? Is this particular guy, this language, decidable? Okay, so what you need to remember is that it's a regular expression. And so with the regular expression, we can convert a regular expression into a DFA. We know how to do that because regular expression to DFA is Thompson's construction, or regular expression to NFA is Thompson's construction. We know how to do that. Then NFA to DFA, you can use subset construction. And so since I have the answer for NFAs and DFAs already, I can run them as subroutines. So you can kind of see here that you can decide either A or B depending on your mood about it, but it follows immediately because I can use my subroutines, or you can say, well, putting this together is a lot of work, and so it's possible, but it requires additional work. The only answer that's not very good is that intersection is not a regular operation, because it is. Okay, so moving on from regular languages, we now want to talk about context-free languages. Let's say I have G, it's a grammar, and then I have a language, I have the language that it creates, right, L of G. I want to know if a particular string is in it. So theorem, AC of G is decidable. Proof, well, as usual, we're going to have to give a Turing machine that decides it. This is where we're going to have to use some techniques to be able to accomplish this. Recall that we have the Chomsky normal form that has a particular way of writing the grammar, and all grammars can be written in Chomsky normal form. All context-free grammars anyway. Since we can convert every CFG into a CNF, we can use that. Now, if H is in CNF form and W, a string, is in L of H, then every derivation of W has 2 times length of W minus 1 steps. So, as usual, we're going to write our algorithm. We're going to say, I'm going to take my input, which is GW. I'm going to convert G into CNF. and then I'm going to try all derivations of length 2 times w minus 1. So even though there's infinitely many strings in this language, possibly, all strings, if you could derive them, you would be able to do it within 2 times w, length w minus 1 steps. I'm going to accept this string GW if any of the outcomes actually generate W, and reject if not. And the important thing to notice here is that because this is bounded by the length of W, I know that this algorithm is eventually going to halt. And the corollary is every CFL is decidable. So let A be a CFL. It's generated by a grammar. And let's create this Turing machine. So this is a little bit different from what I just said, which is had a particular string. And now I'm just saying that if I have a particular context-free language, then it's decidable. In other words, your Poisson automata will never loop. I'm going to run dACFG on GW, and I'm going to accept if dACFG accepts and reject if it rejects. Okay, this is basically just saying I'm just going to run on that string and then accept if it accepts and reject if it does not. And that's it. So here's a question for y'all. Can we conclude that a PDA is decidable? Okay, so as we mentioned earlier in class, PDAs and CFGs end up being equivalent. You can convert one to the other. And so there's an algorithmic way to do that. You would say, okay, this PDA, I can convert it to a CFG, and then I can run it with this Turing machine that I already had. Let's continue on with the emptiness problem for CFGs. All right, so notice that we've already talked about the emptiness problem for DFAs. All right, so G is a CFG. The language of this grammar is empty. E CFG is decidable. On input, the grammar, let's work backwards from the terminals. And again, we're thinking about that idea of reachability. Are those terminals reachable? So I have this grammar, and I have the terminals. And then I want to say, okay, if there's a rule that takes me directly to a terminal, can I reach that? Moving back, I go back and I say, okay, I could have reached those terminals. And so you might conclude that that language is not empty. So the overall idea then is to mark all occurrences of terminals in G, repeat until no new variables are marked, and then mark all occurrences of variable A if all the BIs were marked, and A is a rule that goes to B1 through BK. So I can cross out A if everything on the right-hand side was already marked. Reject if the start variable is marked, because that means from the start variable I could get to a terminal. Otherwise, I will accept. So now let's talk about another problem, the equivalence problem. And this is the equivalence problem for CFGs. So we just talked about the equivalence problem for DFAs. And we saw that we could use the symmetric difference of two DFAs and then run the empty decider to see if that was, if the languages were the same. And so looking at this, I say, okay, I have two CFGs and I just want to check if the languages are the same. Is it possible to do that? Can we use the same strategy? Well, it turns out you cannot. EQ CFG is not decidable. So EQ CFG is saying G and H are CFGs and the language of G is equal to the language of H. Now, thinking about the fact that we have a CFG, we could convert it to a PDA, but here's the thing. CFGs are not closed under intersection, and so they're also not going to be closed under symmetric difference. I'm going to skip the proof for this moment, because to prove things are not decidable, it's a little bit different than proving that things are decidable, because I literally can't have an algorithm. I need to prove that you cannot create one. We'll get back to it. Let's look at one more question of a similar type. Let ambig of CFG be the set of grammars where G is an ambiguous CFG. And it turns out that this guy is also not decidable. And I wrote, it's also going to be skipped for now. We'll come back to it at some point, maybe through homework. Let's do a quick question just to see how you're coming along. Make sure you understand the answer to this question. Why can't we use the same technique that we use to show EQ DFA is decidable to show that EQ CFG is decidable? And I have here A, because CFGs are generators and DFAs are recognizer, B, because CFLs are closed under union, and C, because CFLs are not closed under complementation and intersection. Okay, this is a really good question, actually, because A is true. CFG is a generator and DFAs are recognizer, but it's not the reason why. Because CFLs are closed under union. That's also true. CFLs are closed under union. So the answer ends up being C. The fact is, CFLs are not closed under intersection, they're not closed under complementation, and therefore, they're not going to be closed under symmetric difference, and we can't use that same proof technique. All right, so we just saw an example of an undecidable problem. Let's bring ourselves up a little bit more and put a Turing machine inside another Turing machine. This is ATM, which is the acceptance language. It's the set of M, a Turing machine, and W, a string, where M accepts W. And it turns out that ATM is not decidable. And we'll skip the proof for this moment so that we can talk about the fact that it's recognizable. To make something be recognizable, all you have to do, as usual, is to create a Turing machine. It's just a Turing machine that is not a decider necessarily. It could be, but in this case, it's not going to be. This Turing machine, U, is going to recognize ATM, and we named it U because it's universal Turing machine. On input MW, we're going to simulate M on input W, and then we're going to accept if M halts and accepts. That's it. You just run M on W. And we'll reject if M halts and rejects. And then we have this line I said reject if M never halts. That's not legal. This is the idea of the universal computing machine, which comes from Turing. That this idea that you can put a Turing machine inside another Turing machine. He didn't call them Turing machines, but that is what we are doing. And John Voigt Neumann said that U just inspired the concept of a stored program computer, which is exactly how our computers nowadays work. So let's go ahead and just review, just summarize what we just talked about. I showed the decidability of various problems, A DFA, A NFA, E DFA, EQ DFA, A CFG, and E DFA. So you should know what these languages are because they might be used on homeworks or exams, and you can use the results about them right away. So if you need to show that a new language is decidable, you can definitely run any of these decidable languages. You can run the Turing machine for them as a subroutine if you need to. And then the last thing that I did was show that ATM is Turing recognizable, but of course it turns out that it's undecidable. All right. So I skipped it for the moment, but let's come back to it. Now we're ready to start talking about undecidability. ATM is the acceptance language, MW, where M is a Turing machine and M accepts W. And it turns out that it's not decidable. So to prove that something is not decidable, we are going to use a proof by contradiction. This is going to say, let's assume that it exists. And then we're going to do some stuff, and then we're going to show that it could not have existed after all, and therefore a contradiction. So, H takes MW, and it accepts if M accepts W, and rejects otherwise. Right? We have a recognizer for this, which is just to simulate, but that we didn't know what to do if M was going to loop forever. Now, we're going to use H to construct a Turing machine D. D is going to say on input M, simulate H on input, and then the input is M, and then M taking itself as input. It'll accept if H rejects, and then reject if H accepts. So the important thing here that I want you to think about is that it's doing the opposite. So it accepts if H rejects, and it rejects if H accepts. So, in other words, D accepts M if M doesn't accept M. D accepts D if D doesn't accept D, because you can run Turing machines on themselves. Contradiction. You might be wondering why this proof is called a diagonalization proof. So I said D for diagonalization. Let's look at what diagonalization means. Thinking about the fact that Turing machines are innumerable, right? So it means that I can literally list them out, and I can say, this is the first Turing machine, this is the second Turing machine, this is the third Turing machine, and so on. At some point, like maybe the 50th Turing machine is D, right? It doesn't really matter how I've numbered them, but it's somewhere along that list. And so along the thinking about like all of the inputs, you can write this as a table, right? So you can say, I'm on input M1, the machine, and input M1, thinking of it as a string. And maybe M1 on M1 accepts. Maybe M1 on M2 rejects. So going through and filling out this table, there's some way to fill it out. Like, I don't know if M2 rejects M2. Maybe it does, maybe it doesn't. But there's some way to write this out. So looking through, remember D is going to do whatever the opposite is on that machine. So M1 accepts M1, which means D is going to reject on its first input, right? And then on the second input, it's going to accept because M2 rejected M2. And so on and so forth, right? So M3 accepts M3, which means D rejects M3. Okay, so we've built out this nice little table where D is the opposite of all the things until we get to D itself. Because D accepts D, but that means D doesn't accept D, and vice versa. This is a contradiction, and that it means D can't exist at all, which means that H could not have existed. Going back here, we started with H, and if H doesn't exist, then it means ATM is not decidable. And it doesn't even matter what H is. Like I just said, any Turing machine, it does the thing that I wanted to do, which is decides ATM. I didn't say anything about how it's constructed, and therefore it could be anything, and it can't exist. So let's take a look at this question. We've talked before briefly about the Q automaton, or a two-stack PDA. So the Q PDA is like a PDA, except for it is deterministic in this case, and it has a Q instead of a stack. And then I'm going to have this language AQA, where B is a Q automaton and B accepts W. And my question for you is AQA decidable? Okay, so you might say QA are similar to PDAs and APDA is decidable. Because Q automatons seem like PDAs, and this language, if I replace QA with PDA, I would know that it was decidable. Answer choice B says no, because yes would contradict results we now know. Or C, we don't have enough information to answer this question. Okay, so kind of thinking back to what we talked about with Turing machines, a Q automaton is more powerful than a push-down automaton. In fact, it is just as powerful as a Turing machine. Since it's equivalent to a Turing machine, it's going to turn out that this is the same kind of language as ATM, and it's therefore undecidable. I want to talk a little bit more about diagonalization by talking about infinity. Let's talk about how to compare the relative sizes of sets. Cantor had this idea, right? So let's take a moment and think about two sets. If they're the same size, you can map one item to another item, and they map up perfectly with one another. So that is this idea that A and B have the same size if there is a one-to-one and onto function, f going from A to B. If a function is one-to-one and onto, right, it is an injection and it is a surjection, then that means it is a bijection. Right? So remember that the definition of one-to-one or injective is if x is not equal to y, then f of x is not equal to f of y. Onto is the range of that function, or codomain, as I prefer to say, which is b. And if it's all of b, then it's surjective. This is going to be a one-to-one correspondence. And so two sets have the same size if we can pair up their elements. This definition definitely works for finite sets. You can see if two sets are the same size by just lining the elements up. So let's say I have like some puppies, and then I have some cats, and for each of the puppies, I point it to one of the cats. Okay? Basically, seeing here, I have 6 dogs, and I have 6 cats, right? So the sets are of size 6. It works for infinite sets, too. This is this idea that we can talk about countably infinite and uncountably infinite. So the standard thing that's countable is the natural numbers, because you're literally counting 1, 2, 3, so on and so forth. Now looking at the set of integers, I have negative numbers, -1, -2, -3, but I also have positive numbers and 0. So are these the same size? Yep, they are. You can do this by showing a bijection. What I'm going to do is I'm going to write down and enumerate all the elements of the natural number starting at 1, and then I'm just going to go to 0, then -1, then +1, then -2, then +2. And you can see how I'm alternating between positive and negative here. Because I can keep going forever, it turns out that this is going to be a bijection. More surprisingly, perhaps, is that the set of rational numbers is going to be the same size as n or z. It's also countable. It seems like there should be more fractions than there are natural numbers. Well, all we have to do is show a little bijection. I'm going to show it in this kind of picture. And it's kind of the same where we were with z, where we zigzag between negative and positive. Only here, what I'm saying is 1 maps to 1, then 2 can map to 2, and then I'm going to go to the right, saying the next number I'd like to map to is 2 over 2, but I already did that. So that gets removed, and then I'm going to go up, and I'm going to get 1/2 from there. And so 3 is going to map to 1/2. So basically what I'm doing is I'm going down, and then I'm going to go over in this kind of L-shaped maneuver. So 4 maps to 3 over 1, 5 maps to 3 over 2, then 6 I'd like to map it to 3 over 3, but that's been used, so I'm going to remove it, and then I'm going to go back up to 2/3, and then for 7 I'll go to 1/3. And so basically we're just filling this space out. So it turns out that this is going to be a bijection. And we can keep going for some time on this. You can probably come up with another bijection for this as well. Now, the definition of countable or countably infinite is that, well, okay, a set is countable if it is finite or it has the same size as n. So if I say countable, it means it's either finite or it is the same size as n. And then I might say countably infinite if I want to indicate that it has a bijection to the natural numbers. Z and positive rationals are countable. Well, it turns out, though, that R is uncountable, right? There are more real numbers than there are natural numbers. So real numbers, kind of the way that you can think about this is that between two real numbers, there's always another real number. You can express this by infinite decimal expansion. So my theorem here is that R is uncountable. It's infinite, just like the natural numbers are, but it's bigger than the natural numbers. We're going to do a proof by contradiction. So this is going to be another diagonalization to kind of take this back to how we saw it with Turing machines, that we're doing the same thing here. There is a one-to-one correspondence from f going from n to r. This is a proof by contradiction, so I'm going to assume for the sake of contradiction that there is this function. All right, I don't know what it is, but let's build it out. N, I have my n's, and then I want f of n. Okay, this just goes to like some number, I don't care, 2.718, and then 2 goes to 3.14, whatever. 3 goes to all zeros, 4 goes to 1.414, and so on. Just, it does not matter what this correspondence is. Now, we need to demonstrate that there's going to be a number in the reals that is missing from the list. So let's consider this number. X is equal to 0.8516182. And then I'm going to say 8 is not equal to 7, so I'm going to just subtract 1 from it. 5 is not 4. 1 is not 0. 6 is not 2. 1 is not 5. 8 is not 9. And 2 is not 8. Okay, so I just picked another number that it wasn't. This number, then, is going to differ from the nth number and the nth digit. Okay, so let's highlight this again a little bit better this time, which is each of the numbers that I had in my list, I'm going down via a diagonal to indicate what it is. So that first number I had was 7. I just picked another digit. It wasn't. And then 2, since it went to 3.14, I picked that digit and I said that it wasn't that. So I moved on. And so at each step, looking at my list that I created for my correspondence, I picked a number that at that digit place, it wasn't. X cannot have been any of the values coming from n. It has to be missing from the list. Therefore, there's a real number that is not mapped to, and this correspondence cannot exist. And notice it didn't matter what that correspondence was to begin with. I just picked something to demonstrate it. All right, so we conclude F is not a one-to-one correspondence. This is diagonalization, and hopefully that imagery becomes more clear about why it's called diagonalization, because we're looking at the nth number at the nth digit. So let's continue on with this idea, because we showed the diagonalization argument for Turing machines. L is all languages. The set of all languages is uncountable. If you you can actually do a one-to-one correspondence from the set of all languages to real numbers. Okay, like with languages like we've been talking about, we can write a bijection. So sigma star, though, which is the set of all strings, that is countable. If M is the set of all Turing machines, then you can actually map the set of all each Turing machine to a number. And so it turns out that all Turing machines is countable. because M, such that M is a Turing machine, is inside sigma star. That means that some language is not decidable. Right? If the set of languages is uncountable, right, it's in the size of R, but all Turing machines, the set of all Turing machines is countable, there must be a language that we can't hit, right, a number that we can't hit. And that language, therefore, cannot be decidable. There are more languages than there are Turing machines. We show this with diagonalization by showing that a specific language, ATM, the acceptance language, is not decidable. Okay. So let's ask a little question here for you. David Hilbert asked if there is a set of intermediate size between n and r. So if n is uncountably infinite, then the next biggest infinity up is r. Gödel and Cohen showed that we cannot answer this question by using the standard axioms of mathematics. How can we interpret their conclusion? I think this is a feelings-based question. Either we need better axioms to describe reality, or infinite sets have no mathematical reality, so Hilbert's first question has no answer. I can go either way on this, because it just kind of depends on what you feel like subscribing to at this moment, and then you can change your opinion over time. But one thing that I want to say is that with Gödel's incompleteness theorem, it's actually not possible to have better axioms. There's always going to be stuff that you can't prove. If you kind of go the Bertrand-Russell route, you might say that these kinds of sets are a paradox and maybe like they just can't exist and you're done and you're happy. But we kind of live in the world of A right now. I'd like to talk about the complement of the acceptance language, which is written as ATM with a bar on top. We know a bar as complement. Now, it turns out that the complement of ATM is unrecognizable. So ATM, remember, was recognizable. It wasn't decidable. Now, it turns out that not ATM is actually unrecognizable. You can't even recognize it. The helpful theorem here that you should memorize is that if A and A bar are both T recognizable, then A is decidable. So let's go through the proof. If M1 and M2 are the Turing machines that recognize A and A complement, right, because I said they were both recognizable, then I can make a new Turing machine that decides A. T takes W, which is my string, and I will run M1 on W and M2 on W. At some point, one of them is going to accept, right? Because if A is recognizable, then running M1 will eventually accept, right? Because it always accepts. It might loop forever if X is not in the language, but if X is in the language, it will eventually accept. On the other hand, with A bar, if X was not in A, then X is in A bar. But M2 is going to recognize the strings that are in A bar. So if M1 accepts, then accepts, and then if M2 accepts, then reject. And it turns out that these are all the cases that there are. There is no looping forever because one of them will eventually halt. The corollary to that is that ATM bar is unrecognizable, because if it were recognizable, then ATM would be decidable, right? So looking back at the theorem at the top, A and A bar are both T recognizable, then A is decidable. I already know that ATM is undecidable, which means that it and its complement can't both be recognizable. So ATM I know is recognizable. That means ATM bar is unrecognizable. So you can draw this as a Venn diagram where you take the languages that are recognizable and then you take the complements of those languages, which are called co-recognizable. So not recognizable, but co-recognizable. And you put those together in a Venn diagram. The center of that Venn diagram where they overlap is the decidable part. But you can have languages that are not in that intersection. So a question here for you. From what we've learned, which closure properties can we prove for the class of recognizable languages? Union, intersection, complement, concatenation, and star. And this is going to be a choose all that apply. I'm actually not going to answer this. I'm going to leave it to you to figure out and come through with this one. Next, let's talk about reductions. Reductions is the most important thing that you will learn, in my opinion, as a computer scientist, because it's all about subroutines. We're going to use the fact that ATM is undecidable to show that other problems are undecidable. So our starting language is ATM that we already know is undecidable. I use diagonalization for that. Let's create this other language that's the more famous one, but not even the one that we start with, which is halt. MW, M halts on input W. This seems like it should be easier because they don't actually care about accept or reject, just does it stop. But it turns out that halt TM is undecidable. We're going to do a proof by contradiction. We're going to show that ATM reduces to halt. So this is the new kind of vocabulary here. This is an important word to remember. Here is the word reducible. Okay. For the proof by contradiction, you're going to assume that halt is decidable, and then we're going to show that ATM is decidable as a result. We already know that ATM is not decidable, so that will lead to our contradiction. If I assume that halt TM is decidable, then I'm going to have a Turing machine that decides it. We're going to construct a new Turing machine that decides ATM. On input MW, which is what I want for ATM, we're going to use R to test if M halts. If it does not halt, I'd reject. Otherwise, if it does halt, I'm just going to run M on W. It's safe to do so because I already know from step 1 that M on W halts, accept if accept, reject if reject. This Turing machine actually decides ATM, which is a contradiction. It only works because I assumed that R exists. And so I can tell R does not exist, and there you conclude halt TM is undecidable. So, quick review. So let's just pause here because this is a pretty long video. And let's just make sure that we understand why ATM is undecidable, what the diagonalization method is, the fact that ATM complement is unrecognizable, and we are starting to have an idea of what it means to do a reduction. If there are any of these topics that you don't quite get, please go back in the video and watch earlier on. At this point, I'm going to start talking about the reducibility method for proving undecidability and unrecognizability, and then I'll talk about reductions in general. Reducibility is this idea that if we have two languages or problems, A and B, A is reducible to B means that we can use B to solve A. For example, let's say you wanted to measure the area of a rectangle. You already know how to measure the lengths of the rectangle's sides. Well, if you have those answers, then you just multiply it and you've got the area of a rectangle. Another example is that A NFA is reducible to A DFA. We had the Turing machine for A DFA, and then we used it as a subroutine for A NFA. So another way to say this is if A is reducible to B, then solving B gives us a solution to A. Maybe we have to do another operation, but those are sort of simple operations to do to add to the algorithm, to convert. Okay, so B, if it's easy, then it means A is easy, right? So easy means like maybe we do like a couple more steps on top of the answer to B to convert it to an answer for A, but it's not terrible. So B being easy means A is easy. Well, that also means that if A is hard, then B is hard. And more importantly for us, is that idea that if A is hard, then B is hard. So a quick question for you is biology reducible to physics? And this is kind of up to you. Is biology reducible to physics? A, yes, all aspects of the physical world may be explained in terms of physics, at least in principle. Or B, no, some things in the world, maybe the life, like consciousness, are beyond the realm of physics. Or maybe you don't have an opinion on this. It doesn't really matter. Just think about that concept of, is the whole kind of field of biology reducible to physics? Let's talk about ETM and why it's undecidable. ETM is the language of Turing machines, where the language of that Turing machine is empty. Now, we talked before about a DFA and saying that the language of the DFA was empty, and we talked about marking states. And then we also talked about CFGs, and we saw some differences between that being decidable versus what was decidable with DFAs. Now here, ETM is undecidable. You could have a really terrible Turing machine, and it could be very difficult to tell that L of M is actually the empty set. Not just difficult, impossible. To prove this, we're going to do a proof by contradiction. We're going to show that ATM is reducible to ETM. So for the sake of contradiction, we're going to say ETM is decidable, and then we'll show that ATM is decidable, which is false. So we'll say that there's a Turing machine R that decides ETM, and then we'll construct a Turing machine S that decides ATM. So S on input MW, we've seen something like this before, but we know ATM takes in M and W. We're going to, as a subroutine, transform M into this new Turing machine called M sub W. M sub W takes in input X, and if X is not equal to W, we'll reject it. Otherwise, we'll run M on W and then do whatever M does. MW works like M, except for it rejects strings where X is not W. In other words, it's only really going to run on one string, which is that particular W that we care about. So L of MW is going to be W if M accepts W. It's going to be empty otherwise. And now we said R existed, so we're going to do R on MW. Now, if MW is the empty set, then we will find that out. So if we get yes, that means M rejects W. We'll reject. And then otherwise, we will accept. Okay, so taking a look at that, because if M rejects W, then we know that M does not accept W. And in this case, R is always going to halt, because we said it was a decider. So this can't exist. So it means that R could not exist. Let's talk more about reductions. I'm going to talk about this concept of mapping reducibility. A function is what's called computable if there is a Turing machine F where F on input W halts with F of W on its tape for all strings W. So with Turing machines before, we've been talking about accepting and rejecting, but the other thing you can think about with Turing machines is what's on the tape when you're done. So with a Turing machine, you can say A is mapping reducible to B if there is a computable function where W is in A if and only if F of W is in B. In other words, we take that string W that was on our tape for A, we transform it somehow to be this new string F of W, and then we can check to see if F of W is in B. So thinking about this in terms of functions, which have domains and codomains, I have W, and W, if it's on the outside, it'll go of A, it'll go to F of W, which is on the outside of B. And then if W was in A, then it'll go to something which is in B. So for example, Um, ATM mapping reduces to the complement of ETM. So A, remember, is for acceptance. E is for empty. All we need to do is turn M comma W into M sub W. And we defined how to make M sub W from MW earlier. So MW says on input X, if X is not equal to W, then reject. Otherwise, we run M on W and we do whatever M does, except if M accepts. Then we can actually argue for this, which is M of W is an ATM, means MW is not empty, right? Because M accepts W if and only if L of MW is not equal to the empty set. This is worth taking time to think about and understanding what that mapping exactly was, because this might be something that you want to use if you need to write a reduction. A mapping reduction might be the way to go to show that something is maybe undecidable. So, thinking about that, the order in which you go to prove that something is decidable or undecidable is going to matter. If A mapping reduces to B and B is decidable, then so is A. So the proof is R decides B. We're going to construct a Turing machine deciding A. We're going to take input W, we'll compute f of W. We will run R on f of W and then output the same thing as what R does. And R decides B, so it's always going to halt. On the other hand, if A mapping reduces to B and A is undecidable, then B is also undecidable. And that's kind of what we've been seeing already with the empty Turing machine language and with the halting language, where we converted one to the other somehow, and then concluded, well, that first one, A, had to be undecidable, and so therefore B has to be undecidable. The kind of caveat I want to give here is just making sure that you're going in the right order when you want to show that something is decidable or undecidable. Another theorem is that if A is mapping reducible to B and B is recognizable, then so is A. That is kind of in the same vein as A is mapping reducible to B and B is decidable. So kind of going between here and here, we can see the original thing that we talked about. We can see that it also applies to decidability as well as recognizability. But the corollary of that is if mapping reduces to B and A is unrecognizable, then so is B. Okay, so quick question here for you. Suppose that A mapping reduces to B. What can we conclude? So does that mean B mapping reduces to A? Does that mean not A mapping reduces to not B? Or none of the above? So this is kind of like a less than symbol. And so when we think about it, like if B is kind of quote unquote bigger than A, then B may or may not be smaller than A. So little a, this answer choice, I believe, is not true for that kind of reason. On the other hand, remember the way that F was working was that it took all things that were in A and put them into B, and all things that were not in A and put them into not B. And so we can see that kind of the same reduction, whatever it was, would work because we have complement here. Mapping versus general reducibility. So mapping reducibility translates A questions to B questions. It's a special type of reducibility. It's useful if you want to prove Turing unrecognizability or undecidability. The general reducibility is when we use that B solver to solve for A. And that's what we kind of started with where I talked about it in terms of subroutines. It can be maybe conceptually simpler, and it's useful to prove undecidability. The noteworthy difference between the two is that A is reducible to not A, but A may not be mapping reducible to not A. So, for instance, not ATM is not mapping reducible to ATM. So you do need to be a little bit careful in terms of which one you use. Mapping reducible is not always possible between languages. General reducibility, you should be able to write those when you're proving undecidability in general. So quick question for you. If A mapping reduces to B and B is recognizable, then is A. Is the same thing true if we use general reducibility instead of mapping reducibility? So for this one, I'll let you think about it and then come back with questions. As with most proofs, we like to have templates because we can just structure our proofs nicely. To prove that B is undecidable, we would show that some A, undecidable, is reducible to B. A lot of times A is just ATM. That's often the easiest one to use, although you can use any of the ones that I've talked about in class. The template is assume there is a Turing machine that decides B, and you construct a Turing machine S that decides A. Contradiction. The real kind of creative and tricky part comes in between how that construction actually looks. So kind of thinking about that, I had to construct that fancy Turing machine M sub W to be able to do that. And so that's what you need to think about as you are doing these undecidability proofs. Now, to prove that B is unrecognizable, you would do show that a unrecognizable A is mapping reducible to B. So for unrecognizability, often a useful language is not ATM, right? So the complement of ATM. Template. Give a reduction function f. So actually showing what that function is. So let's do an example showing unrecognizability so that we can see what mapping reductions look like. ETM turns out it's unrecognizable. So I already did this with undecidability, but it turns out it's unrecognizable as well. ATM, right, with the complement, is going to be mapping reducible to empty. So let's think about that function. My function is just going to take MW, and then it's going to go to M sub W. M sub W is on input X. If X is not equal to W, reject. Otherwise, run M on W and accept if M accepts. And this explanation is that MW is not in ATM, right? It's actually going to accept W if and only if M sub W is in ETM. Right, so let's just say that again. MW is not in acceptance only if M sub W is empty, right? Because the only string I'm even looking at is W. M rejects W if and only if L of MW is the empty set. Let's do this proof where we show that EQTM and not EQTM are both unrecognizable. EQTM is M1 and M2, where M1 and M2 are both Turing machines and the languages of those Turing machines are the same. Both of these are unrecognizable. So remember, the way that we want to prove that things are unrecognizable is by doing a reduction from not ATM. So we have not ATM, and it's going to reduce to EQTM. And similarly, we're going to have not ATM, and it's going to reduce to not EQTM. Now I need to define this guy TW. And remember, I'm thinking about the acceptance language, well, the complement of the acceptance language. TW is going to take input X, but it doesn't care. It's just going to run M on W. TW is exactly the way M acts on W, right? So on all inputs, it acts the way M acts on W. So here we're going to define F. So remember, for unrecognizability, we want to use mapping reduction, and we're going to define an F to help us with that. So F is going to map not ATM problems to EQTM problems. I already have one Turing machine, which is T sub W, so that's T1. Let's think about what T2 is. So here we go. I have M, W, And I'm going to take MW to construct T sub W, and then I'm going to pair it with T reject. T reject is a Turing machine that always rejects. So if I could find out if the languages of these two were the same, that would tell me that TW, that M rejects W. On the other hand, if I have MW and then I transform it, take that function to TW T accept, then I could say, okay, T accept always accepts, and TW means that M is going to accept W, right? And so you can see that they would not be equal, right? So this is very weird in a couple of different ways, which is that despite the fact that these are complementary languages, I'm using the same ATM bar to be able to do my mapping reduction, right? So thinking about that, I think the main takeaway here is just to remember that for unrecognizability, we want to use some sort of function. And no matter what, I think one thing that's really helpful here is just remembering about how to construct from M some other kind of Turing machine that somehow uses W, M and W, if you're starting from ATM or not ATM. So why do we use the word reduce? When we reduce A to B, we show how to solve A by using B and conclude that A is no harder than B. That's that less than or equal to kind of notation. Possibility 1, you bring A's difficulty down to B's difficulty. Or possibility 2 is we bring B's difficulty up to A's difficulty. One would show things are decidable or recognizable. The other one direction shows things are undecidable or unrecognizable. So let's just finalize this video with a review. We talked about the reducibility method to show undecidability and unrecognizability. We defined mapping reducibility. We showed that ETM is undecidable. We showed that ETM is unrecognizable. EQTM and not EQTM are T unrecognizable. And so a couple of things to remember here is for any languages we've proven are undecidable or unrecognizable, you can use those to then prove that a new language that you haven't heard of yet is also undecidable or unrecognizable. And I think that's it. So thank you for watching.